Okay, what do you currently see on the screen? Can you explain in detail?
On the screen, I see a cochlear implant insertion simulator with a 3D model of a cochlea and an electrode array being inserted into it. There are also graphs showing insertion metrics like depth, force, and speed. Anything else you would like me to describe?
Okay, what does the pause button, play and pause button do?
The pause button appears to pause the simulation, and when paused, it will show a play button. What else can I help you with?
What's happening now on the screen?
Currently, the simulation is running, and the electrode array is being inserted further into the cochlea model. The speed and force values in the graph appear to be changing as the insertion progresses. Is there a particular aspect of what's happening that you'd like me to focus on?
How does the autoplay interact with the manual? How does the autoplay interact with the manual insertion?
Based on what I can see, the play button starts the automatic insertion of the electrode array into the cochlea model, as shown in the 3D view. While it's playing, you can pause it, and it seems you can manually drag the electrode array as well. Does that answer your question?
Right, so we're live streaming at the moment. Can you address the viewers directly?
Hello viewers, we're currently looking at a cochlear implant insertion simulator, where we can observe the insertion of an electrode array into a 3D model of the cochlea. We can also see metrics like depth, force, and speed being charted in real time. I hope you're finding this simulation insightful. What are your thoughts on this?
Can you also write an invite for LinkedIn viewers, potential viewers, to join in the live stream?
Sure, here's an invite for LinkedIn. Join us for a live demonstration of a cochlear implant insertion simulator. Watch as we explore the intricacies of electrode array insertion into a 3D cochlea model and discuss key insertion metrics. A great opportunity for anyone interested in audiology, medical technology, or simulation software. Tune in now and bring your questions. How does that sound?
Yeah, that's good, but we're also going to be fixing and working on this website that you currently can see on the screen. So can you update the invitation?
Okay, here's an updated invitation that mentions working on the website. Join us for a live session as we not only demonstrate a cochlear implant insertion simulator, but also work on improving the Bionic Chaos website in real time. See firsthand how we're enhancing this platform for biomedical tools. Your feedback is welcome as we delve into audiology, medical technology, and website development. Tune in and be part of the process. How is this update?
Yeah, that sounds better. Sounds good. And what the website is about? Can you guess?
Based on what I see, the website, Bionic Chaos, appears to offer interactive tools and simulators related to biomedical data and research. For example, there's the cochlear implant insertion simulator we were just using, a biomedical data types explorer, Bounce Viz for demonstrating motion bounce illusions, and other tools for analyzing seizures, simulating hearing aids, and visualizing research papers. Does that give you a good overview?
Can you actually see this drop down menu that I open or not? Can you see this drop down menu?
I'm not able to see the actions you're taking on the screen, so I can't see if you've opened a drop-down menu.
Yeah, that's interesting. And what's the current link? Can you see the link?
The current link I see is bionikios.com/category equals featured plus tools.
So can you indicate any issues with these links? Like I'm not able to share a link like that, do I?
I am sorry, but I do not have the ability to determine if you will have issues with this link.
That's alright. Okay, let's stop that for a sec. Okay, so surprisingly, we're still using Visual Studio Code. I don't know why am I not just developing in the browser. Why am I not just developing in the browser like that? Gemini able to do coding and everything. The tool in AI Studio is actually always result it's always doing React. So I actually give it this image. Give it this image, trying to turn it into a simulation, but yeah, the animations are not great. The animations are meant to be a prosthetic limb simulator connected to nerve tissue. So they're meant to be an electrode interface. Yeah, I'm not entirely sure what's the purpose of it, but this is just trying out the build a functionality in AI Studio. That's the Google one. And it's always doing React, which is a bit annoying, but that's fine for prototyping. Trying to stick to vanilla JavaScript, HTML. Yeah, I like the chat propulsion, works really well. You can move this thing on the screen. Swimming kind of works, doesn't make much sense. Yeah, crawling is meant to be, yeah, bipedal walk, meant to be using only 2 or 3. Should be an explanation at the bottom. Yeah, games like this are nice because you can test what the model can do. This is 2.5 Pro. Yeah, after a while we'll go into this playful mode. Let's just chase these balls. So that's kind of nice. That's kind of nice. Can add gravity so it can actually reach the boat. Okay, so also using AI Studio, but eventually we're doing the development using a GitHub Copilot. That seemed to be the most promising. Seemed to be the more promising. That FME is simulator will actually make it available for you to play with. And we'll run it locally and see what we get out of it. Redeploy. Redeploy. And those live prompts that we use can add overview of the app, how to use and feature improvements. All text should be at the bottom of the page below the canvas. What the okay. Made an error there quickly, but then was able to fix it. And we have an AI advice. I can't actually see the text. It would be nice if you could indicate something specific to fix just by pointing at the screen. I'm not sure about the the original idea probably wasn't quite there. It's essentially simulating a biomedical prosthetic arm over 30 days. But yeah, it's a bit how we're doing. It's nice that you have a AI advisor. Can actually see the text, but it's actually working kinda. Can provide game specific topics like nerve, muscle, electrode health, biogel, or tasks. Your muscle has the lowest at 63%. Focus on tasks like rest or therapy to improve its condition and prepare for future challenges. Yeah, don't really like it. You have this event log, you can move to the next day. It's like too much text and stuff. We wanted something more interactive and more intuitive. So just the fact that the AI can make code that actually works, pretty impressive. Okay, so actually deployed the site. Might have to clear the cache. Might get rid of all of it. Okay, we have nothing new. Oh, the only thing is now the search works with parts of words, not entire. Before it was only doing entire words. Now it's doing parts of it as well. It should actually highlight the word. Collection, collide, collusion, collapse. Okay, that's nice. I don't know why the words are not highlighted. We'll add it to the list. Okay, now we have this Python code testing the site. Yeah, we have this FNIS simulation. That you can play and scroll through, showing 5 different channels. Now the good thing about the Google, the reason we're actually paying for it, it's Notebook LM. So let's start a new conversation. Yeah, we're still on FNIS, but we'll just automate the thing, automate our content creation. So I have this link. Let's see if it will actually be able to access the link. Yes. Might actually. So it doesn't have an image. You cannot add images, I think. Yeah, marketing stuff, whatever. No. We want to describe the web app. So let's do Gemini. There's no speech to text. That's also quite unfortunate. Hey, can you describe this image in detail? It's a front panel of a web application. I want you to tell me what's happening, what is it for? Give a detailed overview of all the parts. Might actually give it another shot. And we'll do the same with Gemini. See which one's better. See which one is better. Hey, okay, are we gonna read it? No, we're not gonna read it. We want, well, we can read it, but we mainly want the notebook LM to just generate audio around it. It's not updating this summary. There was an update button somewhere. Can't see it. Regenerate. Is it when just this text describes web application, and it does say 2 sources over there. I don't think it's updated it. Now it's updating when I refresh the page. Yeah, I don't like dot points. I think ChatGPT has like custom instructions not to do dot points. So obviously Gemini did bullet points, which we don't like. And we want to trash it. We want to trash the. Do we have a prompt like that? Okay, I want it to be critical and analytical, yet fun. We want it to be, yes, I should tell all the issues with it. Where is it? Yeah, that should stop the play when you hit on the event. It just goes to the event at a certain time period. You can show more metadata. It's 10 hertz sampling rate, so on and so forth. So that's kind of nice. You have the explanation at the bottom. Very nice. Well, obviously, I'm not sure how accurate this signal is. And we need a thumbnail for this thing. Hey, can you actually turn that image of the front panel into a thumbnail that doesn't have any text? Let's see who does better image generation. Because we're missing a thumbnail. Should be able to automate all of this. Should be able to just stream without human in the loop.
Welcome back to the deep dive. We're jumping straight into, well, a pretty complex area today. Brain activity data.
Specifically FNIRS data visualization.
Right.
It's fascinating stuff, but yeah, definitely complex.
Right. So our mission here is to really pull apart this one specific tool. It's browser-based, found over at bionicchaos.com, designed to help visualize this FNIRS data. We've got some screenshots, some text describing it.
And we're going to unpack it, what it does, how it works, and maybe why it's useful, or, if it is useful.
Exactly. We'll try to make sense of how it tackles this challenge of showing brain activity. Let's get into it critically, but keep it engaging.
Sounds good. Because the core problem is real, raw FNIRS data. It's just streams of numbers from different spots on the head, changing over time.
A bit of a data avalanche.
Pretty much. Trying to see patterns in that without some kind of visualization. Good luck. It's tough.
Okay, so let's back up slightly. FNIRS, functional near-infrared spectroscopy. Remind us, what's it actually measuring?
Simply put, it's non-invasive. It measures changes in blood oxygen levels in the brain. Specifically, it looks at oxygenated hemoglobin HBO and deoxygenated hemoglobin HBr.
How? Like shining a light.
Basically, yeah, near-infrared light. It penetrates the skull and brain tissue, and HBO and HBr absorb that light differently. The machine detects those absorption changes.
And that tells us about brain activity, because active brain regions need more oxygen.
Exactly. More neural activity triggers increased blood flow to that area. So typically you see HBO go up and HBr go down, relatively speaking. That's the hemodynamic response.
Okay.
But you're getting these signals, these HBO and HBr signals from maybe dozens of locations, all changing second by second. That's the complexity.
Which is why you need a tool like this one we're looking at. So the main feature seems to be this big graph in the middle.
Right, that's the core visualization. It plots those HBO and HBr concentration changes over time.
Okay, so the y-axis, that's concentration. Like how much change?
Yep, usually in micromolar units. It shows the magnitude of the change from baseline. And the x-axis is just time in seconds running through the experiment.
And we see the lines red for HBO, blue for HBr, based on the source material.
Correct. And seeing how those red and blue lines move together, or rather often inversely, is key.
Inverse relationship being the sign of activation.
Typically, yeah. During a task, you look for the red line going up, more oxygenated blood arriving, and the blue line dipping down, more oxygen being used in the channels over the active brain area.
But people aren't just sitting there. They're doing things in these experiments. Tasks, resting. How does the graph show that context?
That's where those colored background sections are absolutely vital. You see them stretching across the plot.
Yeah, different colors, like baseline rest, cognitive task 1.
Exactly. They segment the whole recording into the different phases of the experiment. It overlays the protocol right onto the data.
So you can immediately see, okay, this change in HBO happened during the cognitive task, not during rest.
Precisely. And there are usually dashed vertical lines marking the exact moment of transition between these blocks. It anchors the brain data to the experimental events. Without that, it's just lines. With it, you start to see the brain responding.
Okay, so we know when things are happening relative to the experiment. But the brain has different areas. How do we know where these signals are coming from? FP1, F3 versus, say, T7, T8.
Good question. That's handled by the channels in the legend, usually shown near the graph. Each pair of red-blue lines represents one channel.
And a channel is a specific measurement location on the head.
Essentially, yes. It represents the path the light takes between a specific light source and detector pair on the scalp. The labels, like FP1, F3, or F77, they come from the 1020 system.
The 1020 system, that's standard for placing EDG electrodes, right?
Exactly the same system, mostly. It's a standardized way to place sensors based on skull landmarks, so FP1, F3 roughly corresponds to the same prefrontal area across different people.
And the source says the channels shown here cover frontal and temporal lobes, areas for, like, executive function, memory.
That's what it indicates, yes. Channels like FP1, F3, FP2, F4 over the front, F7, T7, F8, T8 more towards the sides, the temporal lobes, and even one like FP1, CZ connecting front to central.
Okay, but looking at the screenshot, there are quite a few lines already. What if a researcher only cares about the frontal channels for their study? it could get messy.
That's a common issue, and that's what the control panel, typically on the left, is for. It gives you control over the view.
How so?
Well, there's a channels section. It lists all the available channels, each with a little checkbox.
So you can just uncheck the ones you don't want to see.
Exactly. Want to focus only on the frontal lobe, deselect everything else. It really cleans up the plot, lets you focus. There are usually select all, deselect all buttons too, which helps.
Simple but effective. And below that, there's an events list connected to those colored backgrounds we talked about.
Yes, directly connected. It lists the experimental events, baseline rest, cognitive task 1, etc., along with their start times.
And clicking on one.
Jumps the time marker on the main plot right to the beginning of that event. So click cognitive task 1, and boom, you're looking at the data starting from 60 seconds or whenever that task began. It's a navigation shortcut.
Okay, so control over what channels we see, quick jumps to when things happen in the experiment. Then there's another panel at the bottom. Looks like playback controls.
That's right. For interacting with time more dynamically, there's usually a slider you can drag to scrub through the whole session.
Like scrubbing through a video timeline.
Pretty much. And play pause buttons to actually animate the data unfolding over time. You can watch the lines evolve.
Can you change the speed? Real time might be slow.
Usually, yes. There's often a drop down for playback speed, 1x, 2x, 0.5x, that kind of thing. Plus, toggles to show only HBO or only HBR. Sometimes isolating one makes patterns clearer.
And a reset zoom button? I guess you can zoom in.
Oh yeah, essential feature. You can typically zoom with the mouse wheel or pinch gestures and pan by clicking and dragging on the plot itself if you zoom way in and get lost.
Reset zoom brings you back out.
Yeah. And don't forget the status bar at the very bottom. It constantly tells you the current time point your cursor is at, what event.
There's no zoom functionality, by the way, but yeah, we'll get the two hosts to talk about it in a sec. And there is a human in the loop, by the way, so if you have any custom prompts, do let me know.
Block that time falls into, and how many channels are currently displayed. Keeps you oriented.
Okay, this next feature sounds really useful for getting granular, hovering over the graph.
It really is. This moves beyond just seeing the shape of the lines. When you move your mouse over the plot area,
What happens?
a little pop-up appears showing the exact numerical concentration value for HBO and HBR for every channel you have visible at that specific instant in time your cursor is pointing to.
Wow. So the source gives an example around 165.5 seconds during inter-task rest. You hover there, and you see the precise numbers for FP1, F3, FP2, F4, all of them.
Exactly. Think about why that's powerful. You see a bump in the red line for FP1, F3. Hover over the peak, you get the exact value. Is the corresponding blue HBR line showing a dip? What's its value? And crucially, what are the values on other channels, say FP2, F4 on the opposite side, at that exact same moment?
It lets you quantify things much more precisely than just eyeballing the graph. Compare regions, check the HBO-HBR relationship.
Precisely. It adds a whole layer of quantitative detail to the visual inspection.
Okay, so putting it all together, this tool isn't just showing a static image, it's really interactive.
Absolutely. The source calls it a full-featured temporal brain activity navigator. And that seems fair. It's designed to take this messy, multi-dimensional FNIRS data and make it explorable.
Helping researchers see when and where activation happens, how things change from task to rest, compare different brain areas.
Yeah, all of that. It helps interpret those hemodynamic responses in the context of the experiment.
And the source seemed pretty positive about it, calling it dense, but in a good way. Like, lots of info and control, but usable, tailored for the people actually doing this research.
It definitely looks geared towards neuroscientists, cognitive scientists, maybe clinicians who need to dig into this kind of data regularly. It seems to address the practical challenges they face.
And there's even a hint about future development.
Yeah, the source mentioned potential enhancements. Things like adding more data processing options directly in the tool. Maybe filtering, baseline correction.
That would be handy.
For sure. Also support for more data formats, maybe topographic maps, those heat maps showing activity across the scalp.
Oh, that'd be a cool visual addition.
Definitely. And then the usual suspects, better performance with huge data sets, ways to export results or images, maybe user accounts for saving settings, standard improvements for this kind of tool.
Okay, so quite a deep dive there into one specific way to visualize FNIRS data. We've seen how this tool uses graphs, colors, and interactive controls to track brain oxygenation, changes our window into activity during different experimental conditions.
And tools like this are They're really essential. They bridge the gap between raw, complex signals and actual scientific insight. They make the invisible, well, visible and navigable.
Right. Turning that complex data into something you can actually explore and understand.
Yeah.
It helps unlock what the brain is doing during thinking, resting, reacting.
Exactly. Finding the patterns in the noise.
So final thought maybe for you listening. How does being able to see brain activity patterns like this, even as just lines on a graph tied to tasks, change how we think about our own minds, about the link between thought and biology? Consider all the information constantly generated by our brains. Tools like this are the keys, really, to start exploring what's actually going on in there.
We're gonna interact with it? No. Or should we? Can do interactive mode. Then you can't join in. You have to actually start playing it.
Welcome back to the deep dive. We're jumping straight into.
Oh, hey, our listener wants to join in. What's
Yeah,
up?
you mentioned there is a zoom functionality. There is a reset zoom button, but there is actually no option to zoom in and out. So I'm not sure what the button is for. Can you do a highly critical take on this?
That's a really sharp observation. You're absolutely right. The source material mentions zooming capabilities, like using a mouse wheel or pinch gestures, but then also notes the reset zoom button. It's definitely a bit of an oversight in the description if it doesn't explicitly detail how to initiate the zoom in the first place.
Okay, let's unpack this. It's almost like they assumed the zoom function would be intuitive and focused more on the recovery from zooming. Here's where it gets really interesting. Maybe the reset button implies that zooming is possible, just not elaborated on.
Exactly. A highly critical take would be that clear user instructions are paramount for any interface. If a function exists, especially a core navigational one like zoom, the documentation should clearly explain how to use it, not just how to undo it.
So what does this all mean? It suggests a potential gap in the documentation, or perhaps the user interface itself could be more explicit about the zoom controls. It's a reminder that even in seemingly well-designed tools, there's always room for improvement in usability.
Indeed. Now, despite this potential documentation hiccup, let's continue looking at the overall functionalities. We were just getting into the sheer amount of data these tools help visualize.
A bit of a data avalanche.
Pretty much trying to see patterns in that without some kind of visualization. Good luck. Well, it's tough.
Okay, so let's back up slightly. FNIRS, functional near-infrared spectroscopy. Remind us, what's it actually measuring?
Simply put, it's non.
Ah, yeah, uh-huh.
Yeah, can we actually jump into the technical part? And also, can you comment on the fact that it seems like all the 5 channels showing very similar data? Can you address that?
Absolutely. Let's dive into the technical aspects, and that's a great observation about the similar data across channels.
Yes, let's unpack both of those points. Regarding the technical side, FNIRS, as we are about to touch on, measures brain activity by
Detecting changes in blood oxygenation. More neural activity, as you know, generally means more blood flow to that area.
Exactly. So typically you see oxygenated hemoglobin or HBO levels go up and deoxygenated hemoglobin HBr levels go down in active regions.
Okay, so the tool visualizes these changes, these HBO and HBr signals, from different locations on the head.
Right. Now, about your point on the channels looking similar, that could be due to a few things.
Okay, here's where it gets really interesting. What could cause that similarity?
One possibility is that the cognitive task being performed in the experiment might be engaging a fairly broad network across those frontal and temporal areas.
So if the task recruits those general regions, you might see a correlated response across the sensors placed there.
Precisely. Another factor could be the spatial resolution of FNIR. It's not as fine-grained as some other neuroimaging techniques.
Meaning each channel picks up activity from a slightly larger area, so you might see an averaged response.
Exactly. Also, keep in mind the placement of these specific channels mentioned. FP1-F3, FP2-F4 are both on the prefrontal cortex.
Which has a lot of interconnected activity, especially during executive functions.
Right. F7T7 and F8T8 are over frontal and temporal areas, often working together in cognitive tasks.
And FP1CZ is a more long-range connection, but could still show some correlated activity depending on the task.
So while it might seem like the data is very similar, it could reflect genuine broad brain activation patterns for that specific task.
That makes sense. It's not necessarily an error, but a potential reflection of the underlying brain activity being measured.
Exactly. Now, getting back to the tool itself, the main feature, as we noted, is that central graph.
Right, that's the core visualization. It plots those HBO and HBr concentration changes over
The
time.
y-axis shows that concentration change, usually in micromolar units. It's the magnitude of the change.
And the s-axis is simply time, in seconds, throughout the experiment.
And we see the lines, red for HBO, blue for HBr, as the source material describes.
And as we touched on, the inverse relationship between those lines can be a sign of brain activation.
Anyway, that's pretty good. Let's actually download the audio. Might actually use it on the page to do like a more interactive description. I should eventually have both audio and video on the page. Probably normally video is better, isn't it? Yes, so we have the thumbnail. By the way, there is a human in the loop. Well, just about. Just about. Make it the featured. A featured tool to redeploy the website. So it actually appears. Appears on the site. If you have any questions, do let me know. Yeah, the site might be not available for a short time. It's already up there. It's still deploying. Yeah, Gemini did a really bad job at generating a thumbnail, and GPT-4 or whatever with the new Sora, it did a pretty decent job. So thumbs down to Gemini on this one. Okay, so it's there, the thumbnail. It's not available. We need to purge the cache on the side. Okay, now it's there. And when I share, so it's up and running. Hopefully it will get some more relevant ads. Well, relevant to you or the tool, not whoever is currently advertising. And I don't see the thumbnail of this thing. Is that LinkedIn post inspector? Post inspector. Inspect. No, it's not there. Yeah, hopefully it will appear later on. The thumbnail of the image. When sharing, it should come up to this thumbnail, but yeah. And we have a blog about it. Should we actually add it to the page or not? What do you think? What do you think? Because the advantage of audio is that I can just host it on the site, whereas video, I have like an embedded YouTube box on the page. Yeah, I tried to use the build function in AI Studio as well. Also from the images above, how accurate, how realistic do you think the FNIS data is? Don't mind being critical. It says it looks textbook. Wait, is this loading the previous conversation, or is it generating a new one? Confused.
Can you change the speed? Real time might be slow.
Usually, yes. There's often a drop down for playback speed, 1x, 2x, 0.5x, that kind of thing. Plus, toggles to show only HBO or only HBR. Sometimes isolating one makes patterns clearer.
And a reset zoom button? I guess you can zoom in.
Oh yeah, essential feature. You can typically zoom with the mouse wheel or pinch gestures and pan by clicking and dragging on the plot itself if you zoom way in and get lost.
Yeah, I'm pretty sure that's the previous conversation. We already downloaded it, so we can only delete. You can't generate a new one. You can have custom instructions to make it shorter. How accurate, realistic do you think the FNIRS data is? So that should be in that third document that we added. There's multiple bots working together. Yeah, this one being overly optimistic, the GPT-4 should be. Do you have custom instructions in there anyway? I don't know. It has to be added to the prompt, I would imagine. It's working on a different browser as well. Should have told it to mainly focus on the third source there, because that one was added last. Otherwise, it's doing a pretty good job. It's pretty sure it's able to replace what I do like 99%. So, good luck to us all. Okay, I've got another 6 minutes from this thing. So let's do it interactive mode so we can interject.
Okay, welcome to a deep dive. Today we're really zeroing in on something I think quite critical if you ever look at brain data visualizations. How accurate, how realistic does that data actually look?
Right. It's a key question. We're looking specifically at screenshots from an FNIRS brain data visualization tool.
Yeah, exactly. We've got an overview of what the tool does, what it's supposed to show, but we also have a critical analysis from our sources looking at the data.
It's just, by the way, it's not actually looking at the images, it's looking at the description of the images. Just so it's clear or clearer.
And those screenshots, asking, well, does it hold up?
And our mission here is sort of twofold. First, just quickly understand what this viewer shows. The basics, the lines, the task markers.
Right. But then the real core of this deep dive, how realistic is the actual FNIRS data shown in these pictures? We're leaning on an expert critique here. Because it looks slick? Maybe. Maybe a little too slick.
That's the heart of it. So what you're typically seeing in this tool is time series data. It's tracking changes in oxygenated hemoglobin, that's HbO, usually red, and deoxygenated hemoglobin, HbR, often blue.
Okay, so signals linked to brain activity, blood flow, measure over time in different brain areas.
Exactly, and it shows this during task and during rest periods. You see channels labeled like FP1-3, F7-T7, often hitting those frontal and temporal lobes' key cognitive areas.
And the viewer breaks it down visually, right? With those colored backgrounds showing cognitive task 1, inter-task rest, things like that.
Precisely. It helps you see the structure of the experiment. Plus, it has interactive bits playback, selecting channels, zooming in, hovering over points to get specific values.
So on the surface, it looks like a pretty useful tool for researchers to see where and when brain activity is supposedly happening. You see those HBO lines generally go up during tasks, HBR goes down.
Yeah, the classic hemodynamic response pattern. Increased oxygenated blood to active areas. The tool's description even mentions how these peaks and dips clearly highlight brain activation.
Okay, but that's where our critique source comes in. It looks textbook perfect, maybe too perfect. Is it realistic? What does an expert eye actually pick up on here?
That is exactly the question the critique digs into. And yeah, at first glance, it does look like the ideal. You've got these sharp, symmetrical HBO peaks mirrored by HPR dips right when the tasks happen. It matches that expected neurovascular coupling picture.
There's always a but.
But if you're looking at this expecting it to be genuine, like VAR or even lightly processed FNIS data from a real experiment, there are some pretty big red flags, according to the critique.
Okay, like what? What's the first thing that jumps out as maybe off?
Well, the signal clarity itself, it's described as suspiciously idealized. Those lines are incredibly smooth, very consistent.
Smoother than real life. You mean real data is usually messier?
Oh, absolutely. Real FNIR's data, especially from humans just doing tasks, is almost always much noisier. You'd expect artifacts from movement, heartbeats, breathing, maybe imperfect sensor contact, little jitters, spikes, maybe some channels just look bad.
Right.
This data looks, well, almost too clean, like it's been heavily filtered, maybe even simulated. It just doesn't have that noisy texture you expect from raw or even typically pre-processed recordings.
Okay, so more like simulated or heavily filtered data. Oh, hey there, what's up?
So does the description, do you actually look at the original image, or are you looking at the description of it? And also, do you think it's actually simulated, or is it synthetic, or is it real data? What do you think? Or filtered real data, or is it simulated? What do you think?
That's a great question. Yes, we are looking at descriptions of the imagery in the tool. Our source provides that critique based on what those screenshots depict.
And in terms of what we think, the critique leans pretty heavily towards the data being either heavily filtered real data or even potentially synthetic, meaning fully simulated.
It's that level of perfection, that too clean look, that raises those suspicions in an expert.
Exactly. The critique uses phrases like suspiciously idealized and says it looks more like simulated or heavily filtered data than raw.
How so?
Well, think about the actual blood flow response in the brain. It doesn't just instantly react the moment a task starts, right? There's a biological delay.
Okay, a lag.
Exactly. Typically, you'd expect a few seconds between when the brain activity kicks in and when you see that HBO signal rise. But the critique points out that in these images, the changes seem to snap almost immediately to the task periods.
Whoa, so there's basically no lag. It just perfectly aligns with the start and end of the cognitive tasks.
Precisely. That tight of a connection suggests it might not be reflecting a natural biological process in its raw form.
Wow, okay. No lag. That does sound a bit too good to be true. What's another red flag the critique mentioned?
The consistency
Oh, yeah, uh-huh.
Did it say no lag, or did it say minimal lag?
That's a really important clarification. The critique actually says there's minimal lag.
Right. It's not saying there's absolutely no delay, but the lag observed is significantly shorter than what you'd typically expect in real FNIS data.
So instead of that 4 to 6 second delay we expect, it seems much closer to the start of the task.
Exactly. It's that compressed timeline that looks a bit suspicious from a biological standpoint.
Okay, that nuance is important. Minimal lag, not no lag. Thanks for pointing that out. What else did the critique highlight?
The third point was about the interchannel consistency.
Okay, unpack this for me. What does that mean?
Well, when they looked at the data for different channels, different sensor locations, the HBO values were all very, very similar.
Almost too similar.
Precisely. The critique mentioned they were hovering within a very tight range of each other.
And that's unexpected. You'd think different parts of the brain, even in the same general area, would be slightly different responses.
Absolutely. There's natural variation in brain activity and how the sensors pick up the signal. To see such uniform readings across multiple channels is, well, unlikely in real-world data.
Okay, so let me try and recap based on what the critique is saying. The general idea of HBO going up and HBR going down during a task, that basic pattern is biologically plausible.
Yes, the overall direction of change makes sense.
But the way it's presented in these specific screenshots seems off if it's supposed to be real, unprocessed data. The signals are too perfect, too smooth.
Exactly, lacking that natural messiness.
The timing has only minimal lag, which is still much less than expected biologically.
Right, that immediate on and off feel.
And the different measurement channels show a level of uniformity that you wouldn't typically see in real brain data.
Precisely. Unnaturally consistent.
So the critique concludes that if this is meant to be an example of real experimental data, it's very likely either been filtered and cleaned to an unrealistic degree, or it might even be entirely simulated to show an ideal scenario.
That's the main point. Now, if the purpose is purely educational, to show researchers the ideal patterns they hope to see, then maybe it has some value.
But it's crucial not to mistake it for what actual real-world FNIRS data usually looks like.
Absolutely. The critique really emphasizes that the realism is questionable if we're considering this as data collected from a cognitive neuroscience experiment.
Which really makes you think, doesn't it? When we see these kinds of visualizations, or really any presentation of data, how important is it to be aware of this potential gap between the ideal and the reality?
It's absolutely fundamental.
And it leaves us with this idea that we should always approach data visualizations with a critical eye, asking ourselves, does this look too perfect? It's something to keep in mind whenever you encounter data in research or even in the news.
Definitely something to think about as we navigate a world filled with data. Thanks for joining us for this deep dive.
It was great having you with us, and we hope this gave you some food for thought about data and how it's presented. Until next time.
Okay, that's really, really nice. I don't think I can do much better than that podcast myself. Well, unless we have an actual another human, you can always do it with an AI. Some of them are not that great. Some of them are not that great. But it's better than nothing. Okay, real quick, why do you think there is a reset zoom function? Do you see, I don't see any zoom functionality on this page. Can you address that?
I think the reset zoom function is there to allow you to go back to the original zoom level in case you zoomed in or out, but I do not see any zoom functionality on this page.
Yes, that's what I said. Can you explain? Can you elaborate on that?
Based on what I see on the screen, the Reset Zoom button likely returns the display to its original magnification level in case you had previously zoomed in or out using some other method. Do you see any other method of zooming?
No, I don't. That was my original point. Is that the problem? Can you elaborate on that?
Okay, so it seems that the slider at the bottom allows you to go to different time points in the data. What would you like to know or understand about the data presented in the graph?
Okay, this one is it's pretty annoying. We'll wait until it's a bit better. But the notebook LM is actually pretty good. I wish you could. I'm just curious that they didn't do like an interaction with it where you are one of the hosts instead of, in this case, you're like calling into the studio.
Ah, yeah,
Can you actually elaborate a bit more? We discussed the zoom functionality, but there is actually a no zoom features. There's only a reset zoom button on the user interface, but I can't actually zoom in and out. Can you comment on that?
That's a really interesting point you bring up about the zoom functionality.
Says
Yeah,
the
we were talking about
same
the interactive nature of the tool, and you're right to press on the specifics.
According to the How to Use section of the tools overview, it does mention that the chart supports zooming,
It specifically says the chart supports zooming, mouse wheel, or pinch gesture.
but you're not seeing that functionality, only the reset zoom button.
That's a very practical observation that goes beyond just the description.
It raises a question about whether that described feature is actually implemented in the version you're seeing.
Or perhaps it's less intuitive than described. Maybe it requires a specific type of interaction.
It highlights the difference between a tool's documentation and its actual user experience.
Which is a really important thing to consider when evaluating any software or interface.
You can have a description of features, but the reality of using them could be quite different.
It makes you wonder if the critique we were just discussing might extend to other aspects of the tool as well.
Absolutely. If a described interactive feature like Zoom isn't readily apparent or functional, it could suggest other potential discrepancies.
So while the documentation suggests you should be able to zoom in and out, your experience indicates otherwise.
It's a valuable reminder that firsthand use and critical evaluation are key.
Thanks for pointing that out. It adds
yep,
an...
yep. I got it. I keep banging on. We got the picture. And the only question is, not sure, what do you reckon? Should we add the those conversations onto the page? Let's say yes. Any objections? No. Okay, let's see, where shall we place them? Okay, we have two of them.
Okay, well...
Maybe some channels just look bad.
Right.
This data
Okay, so this one's talking about signal quality.
frontal and temporal lobes, areas for
And that one is the overview. And let's actually pop them in here. They will appear under the overview on the page. How was it? I really like how it's working. Hey, no, can just do, no, wrong button. Shortcut Control I. Let's do GPT-4o. We just put the name of the file. Okay, that's in production. To check it on the server. Hey, okay, we actually, so we have play for the tool, we also need play for we'll add the two Notebook LM discussions onto the page. So we have this overview. That's missing, is it? Okay,
Welcome
now we
back to
have
the deep dive. We're jumping straight.
So I want to add description to it. Okay, the description should be just part of the same item, part of the same control.
Made changes.
Made changes. Hey, can you also improve the layout and styling for this item?
Made changes.
Made changes. It's like disabled. What? Improve the layout and add styling for this item. Let's do a different model. Let's do Gemini 2.5 Pro, considering how good it is, having a lot of luck. Vivid. Takes a bit longer though. Takes really long. Okay, it shouldn't take this long. And also we're not checking how it works on mobile. Because we forgot.
Welcome back to the deep dive. We're jumping straight into, well, a pretty complex area today. Brain activity data.
Specific.
Yeah, we already listened to it. We also have another one. So that will be an overview. Then we have another one on signal quality. Let's actually use Claude. 3.5 should be fine. Just add the file there. It should, I would expect it. It's the white background color.
Okay, welcome to a deep dive.
Because of that division. Why did you add that? Yeah, now it's better.
Okay, that's where
Ask onset and offset. That's not really typical biologically. It strongly suggests, again, either some very aggressive artificial cleaning or maybe the data was just generated to look that way.
wow, okay. No lag, that's a big one. And the third point from the critique.
This one's about the consistency between different channels and the specific values you see when you, say, hover over a point. The tool shows concentration changes in micromolar units, ml.
Right.
The source noted that
Why is it now like disabled?
welcome back to the deep.
Everything else, it really cleans up the plot. It tells you the current time point your cursor is at, what event block that time falls into, and how many channels are currently displayed. Keeps you oriented.
Okay, this next feature sounds really useful for getting granular. Hover
Don't forget the status bar at the very bottom. It constantly tells you the current time point your cursor is at, what event block that time falls into, and how many channels are currently displayed. Keeps you oriented.
Okay, this next feature sounds really useful for getting granular, hovering over the graph.
It really is. This moves beyond just seeing the shape of the lines. When you move your mouse over the plot area,
What happens?
a little pop-up appears showing the exact numerical concentration value for HBO and HBR for every channel you have visible at that specific instant in time your cursor is pointing to.
Wow. So the source gives an example around 165.5 seconds during inner task rest. You hover there, and you see the precise numbers for FP1, F3, FP2, F4, all of them.
Exactly. Think about why that's powerful. You see a bump in the red line for FP1, F3. Hover over the peak, you get the exact value.
Okay, so I get the picture. I've already read that. So now it's the Notebook LM podcast is essentially available on the page. So you can, while playing the data, actually listen to.
Okay, welcome to a deep dive.
We understand what this viewer shows. The basics, the line, temporal lobes, key cognitive areas.
And the viewer breaks it down visually, right? With those colored backgrounds showing cognitive task 1, intertask rest, things like that.
Precisely. It helps you see the structure of the experiment. Plus, it has interactive bits, playback, selecting channels, zooming in, hovering over points to get specific values.
So on the surface, it looks like a pretty useful tool for researchers to see where and when brain activity is supposedly happening. You see those HBO lines generally go up during tasks, HBR goes down.
Yeah, the classic hemodynamic response pattern. Increased oxygenated blood to active areas. The tool's description even mentions how these peaks and dips clearly highlight brain activation.
Okay, but that's where our critique source comes in. It looks textbook perfect, maybe too perfect. Is it realistic? What does an expert eye actually pick up on here?
That is exactly the question that critique digs into.
Yeah.
And yeah, at first glance, it does look like the ideal. You've got these sharp, symmetrical HBO peaks mirrored by HBR dips right when the tasks happen. It matches that expected neurovascular coupling picture.
There's always a but.
But if you're looking at this expecting it to be genuine, like raw or even lightly processed FNIRS data from a real experiment, there's some pretty big red flags, according to the critique.
Okay, like what's the first thing that jumps out as maybe off?
Well, the signal clarity itself, it's described as suspiciously idealized. Those lines are incredibly smooth, very consistent.
Smoother than real life. You mean real data is usually messier?
Oh, absolutely. Real FNIRS data, especially from humans just doing tasks, is almost always much noisier. You'd expect artifacts from movement, heartbeat, breathing, maybe imperfect sensor contact, little jitters, spikes, maybe some channels just look bad.
Right.
This data looks, well, almost too clean. Like it's been heavily filtered, maybe even simulated. It just doesn't have that noisy texture you expect from raw or even typically pre-processed recordings.
Okay, so more like simulated or heavily filtered data. Got it. What's red flag number 2?
The timing, the temporal structure. It's a bit too neat, too obedient.
How so?
Think about the biology, right? The actual blood flow change, the hemodynamic response that FNIRS picks up, it lags behind the neural activity. It takes time, usually maybe 4 to 6 seconds, for the response to really ramp up after neurons fire.
Okay, a delay.
Yeah. But here, in these screenshots, the HBO rise seems to start almost instantly when the task block begins, and it drops off immediately when the rest block starts.
Whoa, so there's basically no lag. It just snaps perfectly to the task marker.
Pretty much. That kind of immediate, perfect alignment with the task onset and offset, that's not really typical biologically. It strongly suggests, again, either some very aggressive artificial cleaning or maybe the data was just generated to look that way.
Wow, okay. No lag. That's a big one. And the third point from the critique.
This one's about the consistency between different channels and the specific values you see when you, say, hover over a point. The tool shows concentration changes in micromolar units, mmol.
Right.
The source noted that across several different channels shown at the same time point, the HBO values were incredibly similar, all within 0.1 mm of each other.
And that's unusual. You'd expect more variation between different spots on the head.
You definitely would. Different brain regions contribute differently, individuals vary, sensors might have slightly different coupling, plus simple noise affects channels differently. Seeing that level of near-perfect uniformity across multiple distinct measurement channels is, let's say, unnaturally consistent for real physiological data.
Okay, so let me try and sum up this critique. The overall pattern, HPO up, HBR down, during a task that basic shape looks biologically plausible, like the textbook example.
Correct. The general direction and shape are fine in principle.
But the way it's shown in these specific screenshots is suspect if it's supposed to be real data. Signal's too clean, lacks noise.
Yep.
The timing is too perfect, lacks the expected biological lag.
Right. No delay.
And the different channels are suspiciously uniform in their values.
Exactly. Unnaturally consistent.
So the source basically concludes, if this is being presented as a real data sample, it's highly likely either overprocessed to an extreme or maybe just synthetically generated altogether.
That's the takeaway. Now, if it's meant purely as a demo or a training visualization, okay, maybe it serves a purpose in showing the idealized pattern you're looking for.
But it shouldn't be mistaken for actual experimental output.
Absolutely not. The
Okay.
critique is clear. The realism is questionable for actual field-collected cognitive neuroscience data.
Which really brings up a crucial point for you, the listener, doesn't it? When you look at these kinds of visualizations, or any data display really, how vital is it to understand that difference? The gap between a clean, idealized demo and the often much messier reality of biological signals?
It's fundamental, I'd argue.
And it leaves us with a thought, maybe a challenge. If even visualizations designed for experts might show data that isn't entirely realistic, what should we be looking for? What tells can help us gauge the credibility of data displays we run into, maybe in research papers, news articles, or anywhere else? Something to think about.
Okay, let's dive in. We're looking today at something one of you actually shared. It's this really neat interactive 2D simulation. And it stars, well, an octopus.
Yeah, it looks fun. Like, your first impression is just this friendly octopus swimming around, right? A very simple sort of aquatic space.
Exactly.
Yeah.
Seems straightforward, maybe like, a little web game or something. But what we want to do in this deep dive is go, well, deeper than that.
Mm-hmm.
We want to figure out what's going on technically, sort of under the hood, and maybe more surprisingly, how the ideas behind this connect to some really complex real-world stuff.
Yeah, it's kind of amazing how a simulated octopus can actually shed light on some pretty cutting-edge science and engineering. You might be genuinely surprised.
Okay, so let's start with just the basics. What do you actually do when you know, fire this thing up?
Well, you're basically interacting with this octopus, right? It's got 8 tentacles, and the main thing is exploring how it can move, how it behaves in its little world.
And it's not just swimming, is it? I saw there are different modes, different ways it moves.
That's right. That's a really key part. You can actually trigger different locomotion styles. There's jet propulsion,
Okay.
a kind of crawling motion along the bottom. There's even this kind of surprising bipedal walk it can do.
Bipedal.
Man.
An octopus.
Yeah, it uses 2 tentacles, sort of like legs. And then there's regular swimming too. And what you notice right away is how all 8 tentacles are involved, but they coordinate really differently for each style.
Huh. And I noticed you can also just click somewhere or tap on the screen.
Right, yeah. If you click on the canvas, that sets a target point. And the octopus will try to move towards it using whichever movement mode is active at the time.
Okay. And there's something called playful mode.
Ah, yes. If you toggle that on, little items start appearing on the screen.
Like things to collect.
Exactly. Things for the octopus to collect. So it adds this simple, like, goal-seeking behavior. It's not just wandering around anymore.
Now, the bit that really caught my eye were those sliders, the physics sliders. You can actually, like, fiddle with the world's properties.
Oh, absolutely. That's one of the coolest parts, I think. You get sliders for stiffness, damping, drag, buoyancy, and gravity.
And they have default values listed.
Yeah, the source mentions stiffness at 0.10, damping is quite high at 0.950, drag 0.050, buoyancy 0.10, and gravity 0.20.
And playing with those.
It's fascinating
Mhm.
because you immediately see how changing these fundamental physics properties just drastically alters how the octopus moves, how it behaves. It gives you a really visceral feel for it.
Yeah, it's like you're tuning its reality.
Yeah.
And wasn't there an AI thing too? Little spark buttons?
Yes, good catch. There are these little buttons. One uses AI, specifically the Gemini API, to give the octopus a name on the fly.
Oh, no.
And the other button uses the same API to fetch you a random, interesting octopus fact. So it's this little touch of external connectivity.
Okay, so we've got this interactive physics tweaking kind of game-like simulation with AI bits.
Mm-hmm.
It feels quite sophisticated for something that looks so simple, but, what's actually making it all work with the tech?
Right, so let's shift gears to the technical side. What's really
By the way, there is a human in the loop, if you were wondering.
quite impressive here is that this whole thing runs entirely with client-side web technologies,
Okay.
meaning just HTML, CSS, and JavaScript. It all happens right there in your web browser.
So you don't need to install anything, no big servers crunching numbers somewhere. It just runs.
Pretty much. HTML gives it the basic structure, CSS handles the look, the styling, but JavaScript, that's the real powerhouse here. It's doing all the dynamic heavy lifting.
And it must be doing a lot, right? Drawing the octopus, making it move, handling clicks.
It's juggling several key jobs, yeah.
Yeah.
So first, the visuals, the rendering.
Mhm.
It uses the HTML5 Canvas 2D API. That's how it draws everything you see.
Okay, standard web graphics.
Then there's the physics engine. And
Mhm.
interestingly, it's described as a custom simplified engine.
Custom, why not just use like an off-the-shelf physics library?
That's a good question. The source points out it's based on something called Verlet integration. Now, this method is known for being computationally efficient, and it's particularly good for simulating things made of connected particles.
Like chains or cloths.
Exactly. Or, in this case, the octopus's tentacles, these flexible multi-segment limbs interacting with forces. So building a custom engine, probably based on Verlet, likely let the creators optimize it really well for simulating those tentacles specifically.
Got it. So it's drawing, it's running physics.
Yeah.
But the movement itself feels so fluid,
Yeah.
or organic almost. Is that just animation loops playing?
No, and this is crucial. It's not pre-recorded animation. This is a really great example of procedural animation.
Meaning it's generated on the fly.
Precisely. The movement isn't pre-baked. It emerges in real time based on the physics simulation, on your input like clicking, and on the rules defined for how the octopus should behave when it's trying to, say, jet propel or crawl or walk. It's calculating the motion continuously.
Wow, okay. And JavaScript is also handling the clicking, the sliders, the playful mode.
Yep, all the interaction and game logic. Processing your inputs, managing the playful mode state, spawning the items, maybe keeping a simple score, defining how the octopus seeks those items. That's all handled by JavaScript logic.
And the AI calls.
That's the API integration part. JavaScript uses the standard fetch API to make those calls out to the Google Gemini API when you click the A buttons. It happens asynchronously, so it doesn't freeze up the simulation.
Okay, let me try and boil this down. We've got HTML and CSS for structure and looks. Then JavaScript does the drawing via Canvas, runs a custom Verlet-based physics engine for the tentacles, generates movement procedurally, handles all the user interaction and game rules, and calls external APIs. All in the browser.
You got it. That's the core setup.
Right. So this is where we get to that connection you mentioned earlier, the deep dive part. How does this fun octopus thing relate to serious real-world applications?
This is where it gets really fascinating. These fundamental principles you see right here, simulating flexible bodies, how they react to physics, controlling them dynamically with rules, these are directly relevant to some really challenging and important areas in biomedical engineering and biomechanics.
You're saying that figuring out how to control these virtual tentacles, that's like controlling real-world robots.
In many ways, yes. Think about designing sophisticated robotic arms, especially ones that need to be flexible or interact with complex environments. The challenges are remarkably similar.
How so?
Well, look at the octopus simulation. Managing the stiffness of the tentacles, controlling the damping so they don't just flail wildly, coordinating all 8 of them to reach a specific point you clicked on, or to grab an item in playful mode. These are fundamental problems in robotics. Control, coordination, dealing with flexibility and forces.
Okay, I can see that. Like, maybe in robotic surgery.
Exactly. Surgical robots are a perfect example. They need incredible dexterity, fine motor control, often in very tight spaces. They have to mimic or even improve upon human hand movements.
And simulation is key there.
Absolutely critical. Simulating their kinematics, how they move and their dynamics, how forces affect that movement is essential. It's used constantly in designing the robots, developing the control software, and importantly, training surgeons without risk. The problem of coordinating multiple joints in a flexible robotic arm, very analogous to coordinating those 8 virtual tentacles.
Huh. And what about artificial limbs? Prosthetics.
Another major area. Advanced prosthetics, arms, hands, legs, the goal is always to replicate natural human movement and make them feel responsive, intuitive for the person using them.
So you simulate designs first.
Definitely. Simulating different control algorithms, testing how different mechanical designs will behave under various loads, figuring out how to interpret user commands, perhaps from muscle signals. It's all crucial. You can draw a parallel, maybe a simplified one, to how the simulation's tentacles react to forces like gravity or buoyancy and try to maintain stability or reach for a target. A prosthetic needs sophisticated control to do similar things in the real world.
It's not just about building things like limbs, though. You mentioned it connects to understanding how we move. Human movement.
Yes, absolutely. Think about understanding human gait, how we walk. Gait analysis is a whole field studying the incredibly complex, coordinated dance of joints and muscles involved in walking.
And simulating the octopus walking relates to that.
Yeah.
Even his weird bipedal thing.
It touches on the same fundamental biomechanical principles, yeah. Things like maintaining balance, generating propulsion, the rhythm of movement, coordinating different body segments. Even a simplified simulation like this engages with those core ideas.
Okay, but how does simulating gait actually help people? What's the application?
Oh, it's huge in rehabilitation technologies. If someone's recovering from, say, a stroke or a joint injury, or has a condition affecting their mobility, understanding their specific movement patterns is key. Biomechanical models, often built using simulation principles similar to what we see here, are used by therapists and engineers.
To do what?
To design better rehab exercises, for one, or to develop assistive devices like smart walkers or exoskeletons that actively help someone move more effectively or safely. Simulating how different interventions may be applying a certain force with an exoskeleton or using a particular control strategy will affect a patient's movement helps ensure the therapy or the device actually works well.
And you mentioned injury prevention too,
Yeah.
ergonomics.
Right. By modeling how the human body moves when performing tasks, lifting something, using a tool, sitting at a desk, engineers can design safer workplaces, better tools, maybe even improve sports equipment. Simulating the stresses and strains helps pinpoint risks and design ways to reduce them.
Wow. Okay, so it really sounds like the core method here using physics simulation, especially something like Verlet integration for flexible parts, and using procedural rules to create lifelike reactive movement that's like a foundational technique. And it just gets scaled up and made more complex for these biomedical uses.
That's exactly the link. The fundamental concept is the same. Use computers and physics to understand, predict, mimic, or even help out with complex biological movement. Obviously, in biomechanics or robotics, the models are way more detailed, full anatomical accuracy, much more complex physics, higher fidelity simulation, but the basic idea of simulating movement based on rules in physics. It's right there in this octopus simulation, just on a simpler scale.
And the people who made this sim, they had ideas for taking it further.
Yeah, the source mentions a few future directions, things like making the tentacle interactions more sophisticated, maybe they could tangle or push off things better, adding obstacles in the environment for the octopus to navigate, perhaps more complex AI driving its behavior, and of course, enhancing the sound and visuals.
So more complexity building on that same foundation.
Exactly. Each edition would likely leverage the same core physics and procedural animation techniques, just adding more layers.
Well, this has been really eye-opening. It's actually kind of amazing how something that looks like a simple, playful distraction, this octopus sim, can genuinely offer a window into these incredibly complex and important scientific areas, robotics, biomechanics. These are huge fields.
It really does highlight how powerful simulation and simplified models can be, doesn't it? They're tools not just for fun, but for exploring and understanding really intricate systems like biological movement.
It definitely leaves you thinking. I mean, if the basic ideas behind simulating an octopus can help inform how we design surgical robots or next-generation prosthetic limbs, well, what other unexpected connections are out there, hiding in plain sight between things that seem like play and things that are, cutting-edge science? Something to chew on.
By the way, if you are a human and you want to join the live streams, whatever, I'm happy to pay you as much as I pay for Gemini or ChatGPT. More than happy to put an offer in writing. Just let me know. So currently we're trying to fix the styling of the page. So we're using the style CSS file for which we have for the entire website, and we want the current HTML page work with it correctly. So we're not changing the global CSS file. We just want to change the components, the styling of the components in this particular page that are missing from the global CSS file. Not sure what it will do. Hopefully it won't start changing the CSS. It should be just changing the HTML. Suppose I have too many buttons. Who likes too many buttons? And yes, we already have it deployed, so you can go check it out.
Okay. I will provide the necessary CSS changes to be added to your HTML file. These styles will address missing styles for specific components on the page and resolve conflicts with the global styles.css for the navigation bar, without altering the global CSS file itself. Here's a step-by-step description of the changes. Navigation bar styling asterisk adds specific styles for the navigation links, header nav.nav menu A, to ensure they display correctly and override conflicting styles from the global header A rule, like width, display, text transform, font weight. Simulation can
Okay, first I can do it quietly. Secondly, I'm surprised it's touching the navigation bar because that's exactly what we have the global styling for. Yeah, don't like it. Wait a sec. First of all, let's use a simpler model. For all will do. With discarding changes. Okay, so we have the global Yeah, I thought it was pretty clear prompt. Maybe don't add a styling section, just add styling to each individual component throughout the script.
index.html. Add inline styles to components in the HTML file to ensure compatibility with the global CSS file.
Yeah, I'm not sure about the... Not sure if it actually understands what I meant. Yeah, can we ignore the header? We should also ignore any components that are already present in the global CSS file.
Index.html. Add inline styles to components.
Okay, I can do it quietly. Okay, so it left the header as is. It didn't add the styling section, which is good. Okay, now it's trying to add colors that we have in the global styling file, which might not work. The editor is currently read-only, so you can actually make changes yourself. You can work with the agent together at the same time. This actually was originally made by Gemini. As in within the AI Studio, because they have the build functionality. Or was it? No, sorry, I think it was ChatGPT. I don't remember. It was either or. Okay, so you got rid of 581 lines of code. Why? No. Why being lazy? Don't like it. Which model can do it properly? 3.7 Sonnet. Why is it working this 8 files? It should be just the global style and the Octopus 2D HTML code. 3.7 Claude is not a reasoning model, is it? Because they have 3.7 thinking, which I assume is a reasoning model. Also had the prototype for sound, because we were talking about adding audio sound effects to this thing. It's always adding DSX file, which is can't get rid of it. Yeah, 3.7 Sonnet did the same thing where it got rid of all the code for whatever reason. Question is, can we just do all the coding? In a browser? Well, probably had to split out the JavaScript. I'm not sure when I accept changes in here, does it remember that it got rid of 800 lines of code? I'm actually not sure. Can we delete this? Can we rename things? That looks like. Can we preview? Yes, it's working. It has a CSS, does it? Can you just drop stuff into it? Yes, you can. This now work. No, it won't. Yeah, wait a sec. So it actually looks pretty promising. If we could get rid of Visual Studio Code, that would be greatly appreciated. Okay, why wouldn't it play this? Something in the margin. What? Maximum size of 10 megabytes for apps saved to drive. The podcast file, it's, yeah, 30 megabytes. What? Why? Really? It says that save, but it wouldn't let me save because the project is too large. Okay, that's not very helpful, is it? Yeah. I can get rid of y. Why don't we just able to delete this? No. Yeah, I'm not sure it will work. It simplified the thing, but they got rid of all the code. So let's do Gemini 2.5. I have the files to retry. Yeah, I'm not sure if a human developer would have done much better. Okay, Gemini 2.5 seem to get it. It's not generating code yet. Okay, anyhow, anything we do eventually is on biomedical.com. So go check it out. Let me know what you think. And I'll see you next time. Bye.